Hi, everyone. Thank you for joining our talk on our small project titled Exploring the Use of Large Language Models for Generating Decision Logic and Smart Contracts for Healthcare Processes from Natural Text. My name is Inwan, and we're from Rensselaer Polytechnic Institute. So to start off, we should cover the preliminaries. What are LLMs and how can we use them? Large language models, LLMs, are machine learning models trained on a large data set of text. And there are some very well-known examples in the open already, such as OpenAI's ChatGPT, Microsoft's Bing, Google's Bard, Meta's Llama. And these models introduce a new way to process large amounts of data. However, while these models are very nice, when using these, one needs to keep in mind that LLMs are mostly reliable for mimicking human conversation, summarizing documents, translating between different languages, paraphrasing and or assisting in writing. However, they are not reliable for providing only factual information, doing logical tasks, and or providing bias-free information. Thus, when using them, it's essential to design specific tasks with the correct goal in mind. So what we did was to parse decision logic from healthcare documents. Many parts of healthcare and healthcare-related logic is encoded in a large text document, which the providers parse to decide on the final outcome. And sometimes different providers need to communicate with each other to make a settlement. So what we tried was to divide the whole process into 3 steps. First, we used the LLM to generate a structured summary of the document. Then we used the LLM to encode the text documents and the summary into a formal logical syntax. We tried notation 3 and clinical quality language. And then we translate the logical syntax into smart contracts, which are programs that can be published on a blockchain for interoperability. And each step you'll notice here is constructed with increasing order of complexity to ensure the model is correctly working. So here's what we did for writing the prompt. We asked the LLM to assume a role and provide the specifications in a list. And the input is wrapped in a clear delimiter. And what we do is actually similar to what LangChain does. If anyone's interested, the link is below. And what we find in our experiments is that the LLM is able to perform well on the summarization task. However, as we go to the later steps, we notice some inconsistencies. The modeling can vary, details can be misunderstood or be missing, and the syntax is not always consistent, which can lead to a lot of problems in real life. And when faced with controversial topics, such as the gender, the model may start censoring itself. So what can be done to improve? A specialized version of the model that's fine-tuned for the particular tasks may work better, or more human-generated examples as part of the prompt, or a method to integrate human oversight into the process for the LLM to expand upon. Thank you for listening, and that was a quick overview of our project.
Hello, this is Xia Jing from Clemson University. On behalf of all my co-authors, I'm going to present our project to develop computable clinical decision support rules based on CDC recommended vaccination schedule. Clinical decision support systems have been adopted for a long time, especially in large medical institutions. CDSS are very important in delivering safer, more efficient and higher quality clinical care. But there is a problem is the challenge is we don't have shareable, reusable, computable CDSS rules across the institutions line. So our collaboration is aiming to use ontology to leverage CDSS rules, make them computable and reusable, particularly for resource-limited primary care settings. So currently, we have starting point is vaccination recommendations, endpoint on machine processable format. Based on literature review and our experience, we need at least 2 more middle layers in between the starting point and the endpoint. The 2 more middle layers are tabular format to represent CDSS rules. And the other format is formal language format to represent the logic of CDSS rules. The whole purpose to have those different layers are to make sure the CDSS rules are accurate from the human readable format until to machine processable format to minimize possible errors generated during the process. This diagram shows you high-level implementation plan about our project. Start from CDC recommendations, then tabular format. We have over 500 rules for 19 vaccines. Then use the logic expressions to generate different programming language related rules. Then rule engine will process the rules and patient data to generate recommendations. These diagrams show you on where we are now. Currently, we are using CQL, clinical quality language, to represent the logic expressions for CDSS rules. Then we use JavaScript to write those rules based on HL7 file resources. So basically, we have rules generated. Then we use patient data to look at patient by patient based on their data and the rules condition. The work is ongoing. This is a NIH-supported R1 project, partly supported by P20. And this is our project URL and our contact information. Thank you very much for your attention.
Hi, my name is Simi Sen. I'm a student researcher at Dr. Sophia Wang's lab, and I'm excited to share the work we did using artificial intelligence to automatically compute performance metrics on cataract surgeries. So some background. Cataracts are the leading cause of blindness worldwide, and while cataract surgery can restore the vision, skill factors like time and poor instrument control can affect the outcome. This is why the surgical training process is so important, especially during residency. Right now, trainee surgeons just receive qualitative, mostly verbal feedback from their supervisors, and they don't get objective quantitative feedback on their surgical performance. So the purpose of our study is to evaluate the correlation between surgical skill ratings that we were able to generate with AI and that of expert raters. So we gathered 28 routine cataract surgical videos from residents and 29 from board-certified ophthalmologists. We used our previously developed YOLAC deep learning model to generate granular information, like we were able to classify the techniques used in a cataract surgery, segment anatomical landmarks like the pupil and limbus, and also identify instruments used in a surgery. We onboarded 3 expert ophthalmologists to assess these 57 videos using the standard OSAX rubric, which has 20 items for grading specific steps and overall performance on a 1 to 5 scale. So we have 6 AI performance metrics. We were able to find the total path length, velocity, and the area of the tooltip. We're also able to find the phacoemulsification probe centration, which is the average distance from the phacoemulsification tip, which is the type of tool used, to the center of the pupil. We were able to find the eye centration, which is the average distance of the pupil center to the screen center. And we were also able to find the zoom level change, which is the standard deviation of the limbus diameter, and that measures the zoom level variation. So for a statistical analysis, we compared attending and trainee scores using t-test. We also did a Pearson correlation between OSAX and AI metrics, and we did this in 2 ways. We were able to find the AI metrics versus the overall OSAX score, which is out of 100, and then we were also able to correlate AI metrics with specific related OSAX items, and these are 2 examples of the ones we found. So for our results, we did indeed find that there is a statistical significant difference in OSAX ratings between attending videos and trainee videos. We also were able to find a Pearson correlation between AI and human ratings, and most of them were statistically significant. So this means that AI metrics can differentiate between attending and trainee surgeons, and this is great because we can quickly provide automatic, objective, standardized surgical feedback that will pinpoint and allow surgeons to improve. Thank you so much for listening, and feel free to contact me.
Hi, everyone. I'm Joshua. I'm presenting PhacoTrainer, a deep learning web platform that's aimed to improve cataract surgical training and to facilitate future research on cataract surgery. So cataracts are the leading cause of vision impairment worldwide and the most commonly performed surgery in the United States. Surgical training has traditionally relied on preceptor-led feedback in the OR, and our goal with PhacoTrainer is to leverage the power of deep learning to deliver objective and granular insights into surgical performance. The backbone of PhacoTrainer is a CNN RNN model that's been trained on 268 cataract surgical videos performed by 12 surgeons. And the model classifies 14 different surgical steps, providing a frame-by-frame determination of which surgical step is being performed, enabling the calculation of time spent on each step of surgery. And this provides a new avenue for objectively assessing surgical skill. So given a cataract surgical video, we're able to create and annotate a timeline of the entire surgery, allowing surgeons to monitor their surgical performance across multiple dimensions and identifying areas for potential improvement. In addition, PhacoTrainer can also collect metadata for each surgery, not just for future reference by the surgeon, but also for enabling future studies from a more nuanced understanding of surgical techniques over time. The PhacoTrainer platform also provides a dashboard that displays insights into your surgical performance. We can display graphs not only of individual surgical steps, but of also entire surgical operating times to visualize how these times change as a surgeon gains more experience. Additionally, we're also able to search all the videos processed by PhacoTrainer for specific surgical steps that have been performed. So these metrics are useful for self-assessment as well as identifying areas that could use some improvement. PhacoTrainer is a significant advancement in cataract surgery training and transforms unstructured cataract surgical videos into computable insights. By leveraging deep learning to objectively analyze surgical videos, it provides surgeons with a tool to self-evaluate their skill, track improvements, record surgical metadata, and ultimately improve surgical outcomes. The goals of PhacoTrainer are to democratize these insights, facilitate a more nuanced understanding of surgical techniques, and to catalyze future research on cataract surgery through metadata collection. Thanks for listening.